Thank you very much. Awesome to be here. My talk will be based on ongoing work and work that appeared a few months ago with my student Siwei Zhang and some ongoing work also with Shuji Yang. And the topic is about flux tube interactions in Yang-Mills theory. So I think a lot of people in this collaboration and in general, people interested in confinement have been thinking about the dynamics of flux tubes. So that's why I chose this topic. So I'll just quickly go through the trivial remarks. Many interesting systems admit interesting excitations. Many systems admit interesting excitations which are extended and they're finite tension. So we have the Abrikosov string in superconductors. We have the closely related Nielsen-Olsen string in the Higgs model, in the abelian Higgs theory. We have, of course, confining strings in Yang-Mills theory. And this is a very important discovery of the 20th century, that such excitations exist. Now, what I'm going to talk about is that on the lattice, it's very clear from numerical simulations, especially by Andreas and Mike, who are in the audience, that flux tubes are like single particle states. So by single particle states, I mean that if you, for instance, ask about their energy as a function of momentum, they obey a dispersion relation, like a one particle state. So the energy would be k squared plus m squared in square root, if you give them some center of mass momentum. And the purpose of this lecture is to try to examine why is this even true. In interacting quantum field theories, it's somewhat rare to see one particle state. Sometimes one particle states are unstable and there are interactions. So we're going to try to examine why is it even a thing that's happening. So I'm going to try to discuss what are the interactions between flux tubes to try to understand why these string states look weakly coupled. So we're going to try to determine the string self-interaction. And it turns out that we can understand the interaction between flux tubes without any additional input almost. I'm going to use some kind of approach which you can call the bootstrap. It's basically modular invariance of the string worldsheet. So we will be able to compute interaction strengths. There will be some open questions that we can't answer yet. And then there will be some applications for the baryon junction as well. So let me start with a just quick reminder. We know the effective action for very long flux tubes that are suspended between two Dirichlet boundary conditions. You can think about the Dirichlet boundary conditions as external heavy quarks. And I'm think about pure Yang-Mills theory. These are external heavy quarks. You put them in the system, they create a flux tube, and this is the effective action. And a lot of people in this collaboration contributed to understanding how to quantize this theory. What does it predict? What are the excitations? I'm not going to go over it. I don't have time. So the spectrum to first approximation is just that of like two Dirichlet boundary conditions, waves between two walls. So you get n pi over L, where L is the spatial size of the string. And you have to build a Fock space. So the space of excitations of the flux tube is a Fock space of that sort. And an important idea that I'm going to be using again and again is that you can interpret this computation as a quantization going vertically in this picture. So you have a string suspended between two external quarks. But another interpretation of the same Fock space and the partition function can be done in the horizontal direction, where it looks like a propagator of a closed string to another particular closed string. And in this channel, you don't a priori know what closed string state you are dealing with. You have to try to compute it or bootstrap it. But you know the spectrum of, you know the spectral density. These are just excitations of the closed string. And so this is an important equation that you can have an interpretation when time runs horizontally. And there is a Bessel function here because that's the propagator of a particle in d-1 space-time dimensions. And then these pre-unknown coefficients, v lambda squared, they're characterizing our ignorance of what exact closed string state we create by putting an external quark. Okay? So this is an important idea of thinking about these excitations of the string in two different ways. And just from consistency, we can determine some data about the closed string state that corresponds to an external quark when you quantize it this way. Okay, so today I'm going to talk about a variant of that, which is key to understanding interactions between Yang-Mills flux tubes. So there will be an open channel and there will be a closed channel. So the open channel is a baryon, but the external quarks, unlike in real baryons, are fixed. They are non-dynamical. It's pure Yang-Mills theory. And they form a junction. This junction was already pointed out in the 70s by Arturo and Veneziano and Rossi. And the idea is that in the open channel, you just put external quarks, they create a flux tube, and the flux tube meets at a junction. The junction is a dynamical object, unlike the boundaries. But the idea of the work that I've been doing in the last couple of months is that in a quantization in this direction, it looks like a scattering process of three closed strings. So if we can understand the scattering process and its amplitude, we will know why are the strings even looking like one particle states. If there are interactions, why can we use the formalism of one particle states? Okay, so that's the idea of the work. And we know that these junctions exist. This is from a recent numerical simulation. They put three external quarks and they see that a junction forms. Of course, the idea of effective filter is that this junction can be modeled to be point-like. If you take a long distance limit, we can think about the junction as a point-like junction. I also wanted to make a comment that thinking about this junction as an independent dynamical object is very important for deep inelastic scattering, especially in the EIC. So this dashed line, this is some kind of deep inelastic experiment, and this dashed line represents what happens to the junction as you scatter a photon from a baryon. So we usually discuss what happens to the quarks, but following the junction is very useful in understanding the outgoing states from deep inelastic scattering. And people make people made some predictions based on this idea.
But it should be dual to quark picture as well, or how it works?
Huh?
No, when you do this picture with strings, right? It's a dual to the standard quark pictures in some way, or no, it's not.
I'm just thinking about the lattice experiment where you insert three non-dynamical Wilson lines, okay? Three non-dynamical quarks, they create a dynamical junction, or you can think about it as a scattering of three closed strings. I'm just saying that these junctions have been observed on the lattice, and they're also used as an interesting piece of the proton. The proton mass is essentially in the junction, not in the external quarks. It's the junction that gives the mass to the proton. Okay, so you have to write an effective filter for the junction. This is a pretty elementary exercise. You have some waves, and you have to understand how waves scatter through the junction. That's in the open channel. So the strings can vibrate, and the waves have to scatter through the junction. So how do we understand how can the waves scatter through the junction? It's effective filter. That's what effective filter is invented for. Effective filter allows you to compute up to some unknown coefficients the scattering process from the junction.
Excuse me, how do you take into account the fact that the junction never exists in isolation? It's always between the
flux tubes.
Yes.
Yeah, so the effective filter is for the vibration of the flux tube. So let's say you start vibrating here. You want to ask how does that wave scatter through the junction? How does it split?
Okay.
So the whole theory is about the fluctuations of the strings and how they scatter through the junction.
Okay.
So you have to write an effective filter, and the main reason that I started working on it is that we've realized that there are no operators with two derivatives at the junction. You can rule them all out. It's a complicated analysis that I'm not going to repeat here. But there are 10 operators that could have been present on the junction. These are localized operators on the junction with two derivatives, and they would have made it into a mess with many unknown coefficients. It turns out that they're all ruled out. We ruled them out by various non-linearly realized symmetries arguments. And the junction, therefore, has only one parameter. So everything is computable except for one parameter. And this parameter is, guess what? Just the mass of the junction. So the junction has some inertia. It has some mass. We don't know what this mass is in pure Yang-Mills theory, embarrassingly enough. But, well, Professor Caselle reported on Thursday that he might have measured it recently. But up to Thursday, we didn't know what the mass is. And so up to this mass, so this mass will be like an unknown in these slides, and I'll just make predictions as a function of this mass. And it turns out that that's the only parameter up to very high orders in the finite system. So there are finite volume corrections, of course. This is a finite system, and if you go to high enough orders in the finite volume expansion, there will be unknown coefficients. But up to the first 4 orders, there are no unknown coefficients.
But if it's just m or dt, then it looks like it's not dynamical, right?
Yeah, it's dynamical. It's dynamical.
Yeah,
so
dynamical.
you see, that's the kinetic term.
I see.
So there is inertia, there is a kinetic term. It's just a particle, and then there are the flux tube waves. So, but there is only one parameter on the junction. So classically, if you're a classical physicist, the junction, these are the quarks. You have to create 3 flux tubes, and they meet, of course, at the minimal distance from this. That's called the Fermat point. It's I'll only discuss equilateral triangles for simplicity. So you can quantize the theory with the junction because there are no unknown parameters. This is the spectrum of fluctuations of the junction. It's not. I mean, you can even think about it as a high school problem. It's not something very complicated. So the frequencies depend on the mass of the junction and on the finite size, and there are no unknown parameters otherwise. If you're a classical physicist, then the energy of this configuration is just the distance to the Fermat point plus the junction mass. Quantum mechanically, the fluctuations of these eigenmodes, of course, give you some zero-point energy. And I think that's the key of how to measure it on the lattice. That wasn't known before. There is a certain contribution that goes like 1 over system size squared that is proportional to the junction mass. And that's how you would make a measurement of this mass. You cannot really measure this term on the lattice because there is a contribution from the mass of the external quarks, which is scheme dependent. So to really isolate the intrinsic mass of the junction, I think you have to measure this term. So that's why it's very important to understand these quantum corrections. And I believe this is what Professor Casella has done. I'm going to skip this slide. And so now you can just compute the partition function. I told you what are the frequencies. We put the baryon at finite temperature, and we just solve the open channel. We compute the partition function at finite temperature. You get an Eisenstein series and eta functions. Of course, the eta Dedekind functions are very familiar. These come from summing harmonic modes. But there are also Eisenstein series here that essentially come from the fact that the eigenmodes have these funny pieces. Okay, so the partition function is this is the partition function of a baryon at finite temperature. And what is, if duality holds, and this is an if, it's a physics argument, it should be possible to reproduce this funny object as a local scattering event in space-time of 3 closed strings. It is highly non-trivial because you have to be able to write it as a product of 3 propagators, an integral over the interaction point, and the integral over the interaction point has to admit a local expansion in terms of delta functions. So contact interactions, S wave, P wave, blah, blah, okay? It's a highly non-trivial constraint, but to test the idea that strings have local interactions, this has to be true. And so you can think that we call it flux tube field theory, a la string field theory. It's essentially string field theory. It measures the interactions between closed strings, but in Yang-Mills theory, okay, not in string theory. So you just try to represent all the possible interactions between closed strings by some cubic action. That's the leading order. There are some quartic interactions and so on. And you try to parameterize the unknown coefficients as CABC. And the idea is to try to use the open channel quantization to determine these coefficients, and then have an estimate of the strengths of the interaction between closed strings. Okay, so this is the idea. Are there any questions? Now I'll show you how that it works, and I'll show you the results for the strengths of the interactions. Okay.
2 plus 1 dimensions because...
It's what?
2 plus 1 dimensions.
Oh, I'm sorry. Yeah, I was thinking when I wrote the slides. I'm sorry. Also, this is misplaced. I was thinking about Yang-Mills theory in 3 plus 1. And therefore, the closed string field theory, in quotation marks, of course, is in 2 plus 1, because these are closed strings that interact, and the interaction is local in 2 plus 1 dimensions, because so maybe a better picture is that you have, instead of thinking about circles that interact, think about straight lines. 3 straight lines that come together. So you want to model it as a local interaction, but in 2 plus 1 dimensions. We're not counting the dimension along the string. Okay? So this is what locality means for string interactions, that it has to be local modulo the longitudinal direction. Because of course the longitudinal direction can interact all at the same time. If they just, okay, so you have to try to rewrite this Eisenstein series and dedicate functions as a sum over local things. Okay, this is Peskin and Schroeder. This is just three propagators, and you try to write this object as a sum over a simple Peskin-Schroeder type integral with unknown coefficients that represent the string interaction vertices. And you must ask if it's true, and it's highly non-obvious that it's going to work, but it does work. And here are so one step that you need to do on the way is to simplify it a little bit. You can just use saddle point evaluation for these integrals. So we use some saddle point evaluation, and naturally the dual parameter Q twiddle appears because we're doing essentially a modular transformation. I'm being a little quick already. I just want to get to the main physics points. So it is possible to rewrite it as a local scattering event, and it is possible to therefore read out the strengths of interactions between closed strings with no additional data. I haven't put anything in, and here I'm showing you the data. What is C000? It's the strengths of the interactions of three ground states. Because when you send in three strings, you have to say in which eigenstate. If you send three strings in the ground state, we have determined the interaction strength without any additional data, except for the mass of the junction. Okay. Similarly, this is C001. That's when two ground states interact with the first excited state of the string, and we have many more. I'll show you a few more down the line. They have some complicated dependence on the space-time dimension. R is the length of the string that interacts. And M is the unknown parameter, which is the junction mass. Okay, and L string is just the tension of the string. So what is the most important physics idea? We see that the interaction between strings goes like exponential of minus the size of the string times the mass of the baryon the junction mass. So it's e to the minus 2 pi rm, and r is the longitudinal size of the string. And guess what? It is not actually known whether the inertial mass of the junction is positive. This is one of the main things that befuddled us, but it is, if you quantize this effective action, unlike ordinary particles, for which if you put negative mass, you get all sorts of disasters. Well, what's the disaster that you get if you have a particle of negative mass? Of course, then it becomes preferential to create it from the vacuum at rest, or some terrible things like that happen. Here, a negative mass is okay. It doesn't violate the unitarity of effective filtering, because if you want to create a baryon junction, you have to create it with three long strings, so it's not going to be very beneficial. It's just negative mass at the junction itself. So this Wilson parameter does not have to be positive. In fact, I skipped a slide which showed, we actually quantized it more carefully. If it's too negative, it does lead to unitarity violations, but it can be somewhat negative without leading to unitarity violations. You can find the details in the paper.
What will happen if you add rigidity to this string?
Yeah, this is, okay, so, okay, I'm starting to rush a little bit, but okay, I started 5 minutes late, so in so the effective action that we're beginning from has an inertial term for the junction plus ordinary Nambu-Goto for the flux tubes. The rigidity is an extremely subleading correction in the large volume limit. It's actually zero by the equations of motion. Okay?
No, but it's relevant.
It's highly relevant, and it's zero by the equations of motion. The equation of motion of Nambu-Goto says that the extrinsic curvature of the flux tube vanishes, exactly. I know your work about the rigidity term. It's a different regime. It's not the regime where there is a gap in the bulk and there are sound waves on the flux tube. It's a different regime. It's not this regime. So the most important idea is that actually the interactions between closed strings don't have to be small. There is no reason why M has to be positive. So you can have extremely large interactions between long flux tubes. And this brings to question of why are the lattice people seeing good closed string states? How is it possible? If long strings have extremely large interactions, exponentially large, why are they seeing closed string states? So we said, oh, wow, that means that we have a new prediction. Since the lattice people have not seen that closed string states undergo extremely violent quantum fluctuations, that means that M in Yang-Mills theory has to be positive, obviously. And well, this is just to say it more precisely. If M is negative, you get unitarity violation. So that's what I mean. If the interaction is too large, if this term turns out to be exponentially large in the string length size, this process of splitting a string into two will just proliferate. It's like a Feynman diagram where the vertex is exponentially large. So in this theory, there will be no single particle states. That's like phi cube theory where the cubic interaction is as large as the mass of the particle. There are no single particle states in these such theories. So we made a prediction that since the lattice people have been seeing good one string states, it means that the baryon junction has to be positive. That seemed to be the logical conclusion. And then we went to the Klebanov-Strassler model to check this prediction. In the Klebanov-Strassler model, you can compute the mass of the junction using ADS-CFT correspondence, and it's negative. We don't understand why. We think that it might mean that the strings in the Klebanov-Strassler model are sick. While Casella reported that the mass in Yang-Mills theory is actually positive, and it confirms what we said. So we don't understand this. I said at the beginning that there is an open problem. We don't understand why the strings in the Klebanov-Strassler model have negative junction mass. It seems to violate unitarity, and I think it means that something is wrong. But I don't know what exactly.
There are limits issue between the Argine and this thing.
So this interaction vertex is cubic. So what we computed, and it was computed by Imamura before, we just verified that he didn't make a mistake, was the cubic vertex between three very high anality strings. Strings of anality 1/3.
Yeah, so those may be.
N over 3.
Yeah.
So if you compute the interaction vertex between very high anality strings, the junction mass can be read out from ADS-CFT and it's negative. In my opinion, it means that something is wrong. Because I believe that the unitarity argument is rigorous. If the mass is negative, there is a proliferation of two string states, and it doesn't make sense to discuss strings. But in pure Yang-Mills theory, the prediction seems to be true, according to Thursday. It is positive, and I just wanted to make one more comment. All the calculation that led to this Eisenstein series was for the equilateral triangle. There you can write simple modes, it's just a high school problem. For the non-equilateral triangles, the modes are a little nasty. I mean, the eigenfrequencies satisfy a slightly nasty equation, and the partition function is much more difficult to write. But if you do that, you can get more data by doing the modular transformation, because now you have 3 modular parameters. You can read out more interactions of closed strings in space-time. So I just showed you one more. This is the 0, 1, 1. So it's the interaction of the ground state of the closed string with 2 excited states of the closed string. And we have many more in some upcoming paper, just showing that the method works. And we can determine many, many cubic interactions of closed strings from this method. So we made this prediction that the junction mass is positive. We computed the spectrum of baryon junctions. And if the junction mass is positive, it posteriori justifies the lattice simulations. It justifies interpreting the lattice simulations as a single closed string with some excitations, but it also shows that there are exponentially small corrections. I think that in following the lattice simulations that many people here did, people did not look at the exponentially small corrections, but there are exponentially small corrections due to the string interactions that would be very nice to measure. And so these are some obvious open questions. This might be already determined. I also got an email from a group in Japan that claims that they computed it and it's positive. So I think this might be close to being determined to compute this Wilson coefficient in Yang-Mills theory. What happens if M is negative? You can ask what phase of this of confinement. If the junction has negative mass, it means that strings are not good excitations, but maybe like in particle theory with large cubic interaction, there are some other excitations that one can identify. The Klebanov-Strassler model poses some puzzle that we have not been able to resolve for all this time. And there is a question for phenomenology. phenomenologists are not typically interested in interactions between flux tubes because when you scatter mesons, the scattering happens through the quarks at the endpoints. But clearly we see from this talk that the interaction between the flux tubes themselves are exponentially small. That's one thing. So maybe it justifies ignoring the interactions between the flux tubes. But nevertheless, it might be interesting to think about it more deeply. So thank you very much.
Thanks for a great talk. I was just thinking what a pity it is that this junction wasn't discovered in Princeton because that So we can't call it the Princeton junction. There already is one. But I actually had a very quick question. I think people who study tetra quarks like this.
Yeah, there are two junctions, Rosner and
I think there is a diquark
Right.
and that from that I thought they deduced the mass of a
Yep.
junction and it was pretty large and positive.
Right. So what Igor is saying is that there is of course a large body of work on what's called the Parton model, and where you can try to estimate the mass of the baryon or a tetraquark from adding up the masses of the endpoints plus the mass of the junction. If you do that exercise across many resonances in QCD, you find that the mass of the junction is 165 MeV. It's positive. This does not agree with the value that Professor Caselle reported on Thursday. It relies on the Parton model.
What value did he report?
2.5 times the string tension. 2.8 times the string tension. But that's what the phenomenologists believe. Yes. That's what the phenomenologists believe is the value. But as I told you, in the Klebanov-Strassler model, it's negative.
But
so
those are like very composite strings. Right?
Yes,
Those,
yes.
those are not elementary.
yeah,
It
yeah.
could be that these
yeah.
composites.
Can I only comment?
Yes.
Our value was evaluated for the SU2 model in 2+1 dimensions.
Okay, so we shouldn't
it might
compare.
Be,
Okay,
it might be
we shouldn't
it is
compare, yeah.
different
In SU3 and 3, we need SU3 and 3+1. Yeah. So
I
yeah.
think our idea.
No, it's what I did try to ask earlier that you mentioned the deep inelastic. Okay, if we are talking about deep inelastic at say large Q square, then kind of the leading structure is just kind of distribution of quarks in the nucleon, right?
Yeah.
But it's indeed interesting, first of all, what is distribution, right? How this string effect influences nucleon on which you have deep inelastic. But in second, I think that if it is there or some kind of...
So the idea of this thing is that what happens in deep inelastic is that the endpoints can start changing. So there could be quark creation from the vacuum. That's what you see here.
Yeah.
That means that there is pair creation from the vacuum and the string breaks.
Right,
But the point is that the junction is like a topological thing.
Yeah.
And the junction stays, so you see? So they follow where the junction goes in the deep inelastic scattering. Does it go with, it goes with the outgoing baryons. The junction has to go with, so in deep inelastic you create a lot of mesons that come from the string breaking, but you also get some baryons. And the junction kind of was not destroyed in deep inelastic and it went on with the baryons. So that's what they use.
Defining distribution in initial nucleon, right? And in particular, for example, what I think it could be relevant to say like high twist effect in deep inelastic.
Okay.
You see, because then you're sensitive
But
to
I
the
just don't,
structure.
it's a kind of,
It's not. I see.
we can discuss it later, but not now maybe. I just have 2 more minutes and I see lots of questions. So yeah.
So is there a relation between the mass of the junction and the sign to the ratio between the string tension of fundamental string and let's say in some other representation with 2 boxes? Because in some situation, if you have, let's say...
Yeah, I understand the question. I would say immediately off the top of my head that no, because in large N limit, the mass of the junction is order... Oh, yeah. Yeah, I cannot say that. That would not be a correct argument. I don't know if such a relation exists. Let me just for now.
But did you study strings?
I see what you're saying intuitively, because you could say that maybe a bound state forms from the two strings due to cubic interactions like that. That's like a Yukawa type interaction or something. But
or if you study probe quarks with other analytic tools.
I don't know. I haven't tried to think about it carefully. Yeah.
Chris,
Okay, Chris.
you're next.
Yeah.
Are there any other holographic DSCFT models you can?
Yeah, so we also checked Maldacena and Nunez, and weirdly enough, the junction mass is exactly 0. It's not BPS. The junction is non-BPS, but it's exactly 0 to leading order in the large N limit. In Klebanov-Strassler, it's negative. We haven't found a model where it's positive. But we haven't checked Witten's model, which is the most obvious candidate. We just checked Klebanov-Strassler and Maldacena and Nunez. Yeah.
Quick remark, in 2+1 dimensions, there is another type of quote-unquote string, which is in essence domain line, domain wall in 2
Yeah, in Ising, yeah.
is domain line, so its mass is linear. So you can mimic it in just scalar theory.
Of course.
Say phi cube or so.
Yeah, with phi cube theory, there is a junction, yeah.
Yeah, and this was done quite a long ago in totally different context by my co-author Tony Tervertus and myself, and we found that at least in phi cube theory, positive M or negative M are possible. It depends on particular details.
Yeah.
So.
Yeah, we did an effective filter analysis. Maybe I can say it now more clearly. The junction can be any positive number. That Wilson coefficient is allowed.
Yeah.
But if it's more negative than minus the tension, then you get into unitarity violation in effective filtering.
Yeah.
But there is a small window where it's allowed to be negative.
Okay.
So it would be interesting to see if your thing falls in that window.
Yeah.
Weirdly enough, the answer in Klebanov-Strassler, which is negative, falls in the window where there is no perturbative unitarity. I should distinguish between non-perturbative unitarity and perturbative unitarity. So if it's too negative, there is a problem with perturbative unitarity. If it's not too negative, there is no problem with perturbative unitarity, but there is a problem with non-perturbative unitarity because you get this proliferation of cubic vertices.
Yeah.
So the Klebanov-Strassler answer falls in the window where it's perturbatively unitary, but I believe non-perturbatively non-unitary.
Okay.
All right. Well,